really glad to see so many people in the last session and the last talk, and it's really great. So I'm also waiting for the talk by Denis Boyer. So please, yeah.
Okay, thank you. So I would like to start by thanking the organizers, and in particular Luca, for the invitation. I'm very glad to be here. And I'm going to talk about anomalous diffusion in the context of preferential revisit models, and also their non-exponential relaxation property. So the topic of the talk has to do with path-dependent processes. So path-dependent processes are processes whose evolution rules are dependent on the whole history of the process. So these are highly non-Markovian models. And there are many tools in physics, like master equation and Fokker-Planck equation, that cannot be used to describe these systems often. And an example is a reinforced, so-called reinforced random walk model, where we can consider, for instance, a lattice random walk with nearest neighbor jumps in discrete time, where the crossing probability is not constant in time, for instance, like 1/2, but depends on the number of previous crossing of the walker of that edge. For instance, if that crossing probability is an increasing function of that number of crossings, so we have reinforcement, for instance, linear reinforcement. So this is a bit motivated by biology initially, like in ant foraging or the movement of bacteria that leave pheromone or chemical signals toward which they are attracted, and therefore they visit part of their trajectory again and again more frequently, especially if we assume that these signals do not evaporate in time, so a lot of memory exists in the system. And for instance, in this particular model, exact results on basic quantity are quite limited, in particular to finite graphs or to the very large time limits. There is some relationship with usual normal Markov random walks in certain random environments, because, for instance, this transition probability tends to some random numbers that satisfy some complicated joint distribution at a large time. And there is a slightly, so that was for the edge reinforced, but there is a slightly different kind of process, which is a vertex reinforced process, which loosely speaking means that familiar places tend to receive a preferential visit or are more likely to be revisited again and then become more familiar. So in this case, the probability to visit nearest neighbor is a function of the number of visits received previously by that nearest neighbor. And this can be also, so it's typically an increasing function of that number. So for instance, a linear. And there are actually many examples in human mobility or animal foraging that shows that the likelihood to revisit a certain place is proportional to the number of visits that the individual has made to this place in the past. And so we've seen yesterday in Michael's talk an example of this type of principle. And in that particular model, so the physics, or I mean the dynamics of this process is even more less understood than the previous one. It's very complicated, and there are some essentially some conjectures. So these processes tend to self-localize on a few sides. For instance, 3 at t goes to infinity, just hopping there and back in a very limited region of space. But some very basic quantities, like the propagator or the mean square displacement, the probability density, are largely unknown for this type of process. So generally speaking, we could ask whether this self-attraction what kind of emerging property that can give rise. So that gives rise to anomalous diffusion. How can we describe some possible localization effects? So that means that even at t goes to infinity, the worker gets localized in a very limited region of space. What are the recurrence and first passage properties? So the kind of question that we, well, in physics ask very naturally for subdiffusive or normally diffusive processes. And also, what could be some biological advantages of using such tactics for an organism? And so here, what I would like to present is a class of exactly solvable processes, at least for some of these quantities, that bring some precise answers to some of these questions. So, and they are so based on linear reinforcement in space. So, a first example, so this is a simple model. So we retake the discrete lattice in 1D and in discrete time. So we have a parameter Q, and we make a mixture. It's a slight variant where we have a mixture of a simple normal random walk process and a process with preferential revisits. And it goes as follows. So at each step, a walker with probability 1 minus Q, where Q is a parameter, makes a nearest neighbor jump, and with a complementary probability reset to a site visited in the past. So one of the important differences with the previous model is that that site J does not need to be a nearest neighbor of I. So we can fly over the lattice and just visit that site. And the probability to choose, so if you choose to use memory, the probability to choose site J is proportional to the number of visits received by J in the past. So in a way, it's a kind of a non-Markov extension of a simple diffusion Markov process under some resetting protocol. So the simplest resetting protocol maybe is when you reset the position to a fixed position, for instance, the starting position or the origin, and that's a problem that was studied some time ago by Martin Evans and Satya Majumdar, and which is actually keeps receiving a lot of attention currently in the physics, in the statistical physics community. So here it's something like similar, except that when you reset, you don't reset to a fixed position, but you reset according to this principle. And okay, so if we want to see, for instance, an example of a trajectory, so for instance, you have position n, which is visited a certain number of times, and at time t, you occupy a certain position n prime, and there is a possibility that you revisit n by a memory step. So if we want to write a master equation, so there is the usual nearest neighbor terms, and plus a memory term, so which is proportional to this probability Q, and where m is the probability to revisit this site by the memory effect, so which by construction of the model is the total time spent at n during 0t for this territory, divided by t plus 1 counting the initial position. So there is an equivalent probability formulation where basically we can choose a time in t prime in the past, so an integer time between 0 and t, and look at the position that was occupied at that time t prime, and the probability that that position is equals to n is precisely proportional to the number of visits of that site. Right? So we can write this as a joint probability. So we choose a time t prime with this uniform probability, 1 over t plus 1. And we choose, so that's a probability that at that time we were at time at the site n, we sum over all the possible time, and we take into account that just at time t, just the current time, so we are in some position n prime, and we sum over all the position n prime. And we see that this is simply the marginal of the single time occupation probability. And so we have a closed master equation for the occupation probability, and which implies, well, which is true, actually, if this parameter q is independent of position, space independent. For any site n prime, you can reset to some position with the same probability, right? So which seems that this equation is solved and is closed, and can be solved by some techniques, one or the other. And so these are the main results. So the first result, so there are two results basically for this free particle diffusing with memory. First, we have ultra-slow diffusion. So it's possible to show that the mean square displacement is given by this exact expression for that particular model. And we see that in the large number of steps, that goes like a logarithm of time. So it is a very slow subdiffusive behavior, or ultra-slow diffusion, because it's not described by any power law. And the second result is that the occupation probability tends at large time to a Gaussian with that variance M2, which is a logarithm. So it can be qualified as an anomalous, yes, Gaussian process, in the sense that we tend to a Gaussian unless we don't have a linear mean square displacement, which is kind of the opposite situation that we would have in this case of anomalous yet Brownian, where we have a linear M2 but not a Gaussian form. So here we have the Gaussian, but we don't have the linear behavior, with very slow behavior. Actually, this is approximately Gaussian because there are some corrections that are small only in the limit of very large log t. So we know in practice that this is very difficult. So there are always, in practice, very important correction to that, but I mean, at least theoretically, it tends to a Gaussian. And also, clearly, it's always a time-dependent distribution. So it doesn't converge. It's true for any non-zero value of this probability Q. And so unlike the problem of resetting to a fixed position, which admits a steady state, here there is no steady state, there is diffusion all the time, so it's always time-dependent. And whereas, so the resetting problem to the origin as steady state, which is actually a non-equilibrium steady state, meaning that detailed balance is actually not satisfying that problem. Okay, so this model can be applied to the real life. So these are capuchin monkeys trajectory here in blue on Barro Colorado Island in Panama. So it's pretty much localized. I mean, it's quite looks like a very slow diffusion. And there are some quantities, like the time average mean square displacement or the number of distinct sites, that probably cannot be calculated analytically, but it's very easy to run a computer simulation on the 2D lattice and to calculate this quantity numerically. And actually, we obtain a rather good fit of the data with a non-zero value of Q, and which is basically the only parameter of the model here. And another consequence of the preferential visits is that the distribution of that random variable mi, the number of visits to a site, is power law distributed in the model. So this is very similar to the kind of curves that we've seen yesterday in Michael talk. So basically, a few sites, a very small fraction of sites gets visiting very often, typically near the starting position, and a vast majority of sites, more peripheral sites, receive very few visits. And this is, of course, very different of what we would obtain for a random walk of the same duration. Right? So something that we can try to do next is try to extend this problem to first to continuous time processes, and consider, for instance, an arbitrary Markovian process. For instance, it could be a Brownian motion, for instance, and we have a resetting rate. So during a time interval t and t plus delta t with some probability r times dt, the rule are as follows. We choose a t prime uniformly between 0 and t, and for instance this one, and reset the particle to that position. And then with a complementary probability, just continue the underlying problem. So this is equivalent to implement these preferential visit rules. So actually by doing that over time, from time to time, each time the particle is reset, it will revisit the site with a probability proportional to the local time spent around that site. So a central question is how this new process with memory and preferential revisits is related to the underlying process that we have here, the Markovian process. And actually, this is a relatively simple answer, which is written below. So consider an underlying process, so with r equals to 0, purely Markov process, or close to be Markov process. For example, it could be a random tumble active motion, described by a probability density for the position. So I call it not because r equals to 0, given by a discrete or a continuous sum over some eigenstates, phi of L, that decay exponentially in time with some rate lambda L, where lambda L is an eigenvector associated with this eigenstate. So most, if not all, Markov process can be described this way. So if we have that, then if we switch on memory, the answer is that, so the AL, it basically depends on the initial condition, so it's just a constant. If we switch on memory, so we have basically the same sum, except that the exponential function here is replaced by a more complicated function that depends on the lambda L, which is exactly the same lambda L that we have here, and the phi L is the same phi L that here, and the resetting rate, which appears here and here. And that function M is a confluent hypergeometric function 1 M1, so which is defined as a power series in this way. So if A equals to B, basically it's an exponential function, and one recovers Markovian case. But if A is less than B, which is the case here, then at large time, this function also has a property to decay as a power law of the argument, the negative argument, with a power law A, with an exponent A, as z goes to infinity. Which means that here we will have a sum of modes, of eigenmodes, that we, instead of decaying exponentially fast, they will decay as a power law of time, with some exponent theta L, which is given by that quantity, which is lambda L by r plus lambda L, so which is a number between 0 and 1. So at large time, actually, so this density becomes very slow because it's a sum, it's relaxed very slowly in principle because it's a sum of power laws. And we can try to apply this to many processes, for instance, Brownian motion in a potential, active motion, random walks on networks, or lady flight, and see what are the consequences of this general relation. So, for instance, For a Brillouin particle confined in the potential, so here we have the standard Fokker-Planck equation with unit friction coefficient. Here we have a loss of probability due to resetting, and here again a gain of probability due to revisit of a position because it was visited in the past, which is the analogous of the memory term of the discrete case. So if we consider, for instance, the free case, so the free particle, so we know, so there is, if we apply this recipe, even like the previous formula, so we know that the fundamental solution of the diffusion equation are eigenstates, Fourier eigenstates that decay exponentially with this rate, which implies that, so the theta k that I introduced previously would be, for mod k, would be given by this, and the decay of that mode will be given by that proportional to t to the minus theta k, which is an exponential in logarithmic time. So if we plug it in this sum, so we see that at large time, this integral will be dominated by the small theta k regime, which corresponds to the small k regime. And we see that that's simply the inverse Fourier transform of a Gaussian. Therefore, the distribution here should tend to a Gaussian. And yeah?
Can I ask a question?
Yeah, yes, sure.
So the eigenvalues and eigenfunctions that you showed before, you find it by solving some Sturm-Liouville problem. You can find it, right?
Yeah.
But now you modify the problem. So can you find the effective operator that gives rise to this power law decay instead of exponential decay? Could you identify the effective operator that gives rise to these eigen functions now, new eigenfunctions?
Okay. So I don't know if I understand exactly the question, but basically, the spatial, you can solve this equation by separation of variable, and the spatial part does not change. Yeah. So that gives exactly the same eigenstate. And those are the temporal. No, the eigenvalues are also the same. They are also the same because they are only dependent on the spatial parts. So they are the same. This lambda k, you use that in these two. That is the lambda k, and that is the lambda k. So they are the same. So the only thing that changes is the time-dependent part. So, so it's a kind of a recipe, right? I mean, it happens to be, to actually go in this way. So here we see that, so the variance of that Gaussian will be simply given by d over r by log the rt times 2, which is coincides exactly with the result of the discrete model. So that gives an idea of what is going on. Now, what happened in a confining potential? So, for instance, when we have r equals to 0, so we can write down the Langevin equation, for instance, in the harmonic potential, and so we have a Ornstein-Uhlenbeck process. So actually, in parentheses, apart from the many physical application of that process, actually, it's a OU process are commonly used in animal movement to model in a very simple way home range movements of an animal which is attracted toward the central part. So if there is no memory, so as is well known, so we have in general discrete spectrum of eigenvalue, where the the lowest lambda naught is equals to 0, it corresponds to a stationary state. So we can decompose P as a steady state and the transient part. And the transient part will be dominated at large time by the first non-zero eigenvalue. And so the usual way to solve this problem is to transform the Fokker-Planck equation into a Schrödinger equation by doing this change of variable. And then, so that psi of n is solution of a Schrödinger equation in a quantum potential, which is a transformation of the original potential. So if we can solve this problem analytically or numerically, then we obtain this spectrum. So if now R is different from 0, now we have a spectrum of exponent value between 0 and 1. So we still have theta 0 equals to 0. So the steady state is exactly the same as we have in the usual Fokker-Planck equation, which is the Boltzmann-Gibbs equilibrium. So this is not changed. Actually, it's possible to see that this is actually correspond to an equilibrium state because there is detailed balance that is still satisfied despite of memory. But now the transient part, decay, has a power law of time. And so we do not have any longer, we don't have relaxation, logarithmic relaxation in this situation because there is a gap between the ground state and the first excited state. So at very large time, only that exponent is dominating, is alone dominating the transient part. So we can term this state like a critical state, and theta 1 is given by lambda 1 by r plus lambda 1. So for instance, for the harmonic potential, so we know that the lambda 1 is equal to mu, and so this is the exponent predicted for the relaxation in this problem. So we can also apply, for instance, the problem to a Brownian particle confined in a box of length L with a reflective boundary. So this is an elementary textbook problem of diffusion. So we know that the eigenvalues of the node of cosine modes are decaying exponentially with that rate. And theta 1, therefore, is given by this adimensional number. And so in this numerical simulation, so we show the resetting rate to be twice this leading relaxation rate at large time, so which in this case, so theta 1 is equal to 1/3, and actually see a very slow power law decay, which contrasts with the common relaxation, exponential relaxation of Markov model. So in a sense, this can be considered as some kind of self-organized critical state because it's always happen. There is always a power law for any value of the parameters. The exponent is not universal, and it is a product of the self-reinforcement dynamic of the worker, and a product also of the interaction with the boundary of the system. So there is a third situation where we have a mixed discrete and continuous spectrum. So in the Markov problem, sometimes it happens so that we have the steady state, we have a gap to the first excited state, and then a continuum of eigenvalues. So in that case, the leading relaxation is still given by a power law, but there is a logarithmic factor whose exponent here depends on the density of state in the vicinity of lambda 1, because these states also contribute in a way to the relaxation because they are very close to lambda 1. And this is exactly what happens in the potential. The external potential is just mod x potential, so a force times mod x, and theta 1 in this case is given by this expression. And we see actually in the simulation that if we choose R such that theta 1 equals to 1/2, we don't have exactly a power law relaxation, but it's a little bit faster due to this logarithmic correction. Okay, so following the same line, we can study the large deviation, for instance, for a free particle. So given that we have this general expression, in the large T limits, we can study large deviation. Usually, large deviations so focus on the tails of the distribution. So we are asking what is the probability that the position is, or the modulus of the position is larger than a threshold x. And it is very common that it is an exponential, decays exponentially in time with a rate function here that depend on this rescaled variable. So here for the Brownian particle, so we actually do not see this, but maybe not so surprisingly, we see something where the time t is replaced by log t. So it's a kind of, also we have some anomality in the large deviation. I mean, by calculating a little bit more carefully this Fourier integral. And actually, this kind of law, large deviation law, has been seen in a variety of contexts which are not very related to each other. For instance, the roots of random polynomial or certain problems of random statistics. So here for the Brownian, the free Brownian particle, to stay with Brownian motion, so that function psi can be calculated not explicitly, but it is implicitly given by this expression, which is a Legendre transform, and which can be determined, so we can see what are the small omega and large omega. So it's basically quadratic at small omega and linear at large omega, which means that the probabilities to observe a large deviation depends on two regimes. So we recover the central part, which is Gaussian, if x is lower than the length scale that goes as log t. So we recover the central part, the Gaussian. But we also obtain that for x much larger than log t, the behavior is exponential. So that's the way it looks, that's the way the density looks. So we have variance, a standard deviation that grows square root of log t. We have this length that grows as log t. And then we have this exponential. And quite surprisingly to us, I mean, this form does not depend, this scaling, this function inside the exponential does not depend on time, contrary to this one. And it's actually, the tail corresponds actually the equilibrium state that I mentioned a while ago of the problem of diffusion resetting to the starting point. So so as I said, there is no steady state in this problem, but there is a kind of a hidden steady state at the tail, and which that hidden state disappears little by little as the central part is spreading. And so the interpretation is that, so we have this complicated memory process taking place in the central part, right? Leading to very slow diffusion. And sometimes, from time to time, there is a very rare trajectory, so which has happened with an exponentially small probability that goes very far away from that typical length. And then reset, then we have some typical resetting, then another very rare trajectory, and etc. And where we are at the distance there, so this region looks very small, like a point nearly. So it's effectively as if we had a resetting to a fixed position, and this produces this stationary density. So that's a possible interpretation of this. So, so I would like to draw now to present a different view of this problem, which is in a way a mathematical view of this problem, which is due to these articles. So if we resume what is the type of process we are talking about, so we have a Markov process that starts at time t equals 0. Then we have, it ends, so we have a first run that ends, and there is a resetting, so we choose a time in the past, and we start run number 2. Then run number 2 ends, we have a resetting, so we choose another time, for instance, this one, and we start 3, and so forth, for 4, etc. So when we have, we look at the position at time t, we see that this run 7 was started from a time in the past that was the position, the time t prime that was occurring during run 3. So it's like attaching this piece of Markov process to a previous Markov process. And run 3 was attached to run 1. So each time a resetting occurs, it's like you are adding a node to the system, so a random trajectory. And by choosing randomly a pre-existing node in the system randomly with a weight, because actually the probability to choose a particular node will depend on the duration of the node due to the preferential rule. And therefore, this you are constructing a tree. And we can simplify this trajectory, for instance, we are interested in the position here, by gluing together these pieces of Markov processes. So this piece of 1, then this 3, and then this 3 back directly to 7. And of course, this is a Markov process of a certain direction, capital T, and we know perfectly the distribution of that. The problem is that capital T is a random variable, and we have to sum over all the possible tree configuration and weight configuration. And that was done in these papers where a rigorous central limit theorem and a locality limit theorem were proven in this quite long paper, actually. So it's not Gaussian, it becomes Gaussian in a way very similar to the central limit theorem, even though the process which is underlying can be perfectly Gaussian. So it's only in the limit h goes very large compared to 1. And so there's a large deviation principle analogous to the one that I have described previously, also is equivalent to the result that we have found. So there is a very simple scaling argument here. So we can notice that this time will be at very large time more or less proportional to the 8 of the tree. And the number of nodes will be proportional to time. So we know that in a tree, typically the number of nodes grow exponentially with h. So h goes as log n, which means that capital T goes as log t. So if this is Brownian motion, the mean square displacement will go as a capital T, and it will go as log t. So it's another way of recovering this log t behavior. But this is more general because it can be valid, for any underlying Markov process, in any distribution of intervals between resets, and it can be extended to decaying memory. So for instance, if memory is decaying, so the last added node have a larger weight than the first node, and that can modify this like by log t to the alpha or some t to the alpha or other kinds of anomalous diffusion. So just to finish rapidly, so I would like to see to present how a very slight modification of these processes can give to completely different behavior, in particular localization. And this is done when we have a space-dependent resetting probability. So if we retake the original discrete model, so we have a walker here on this side, the black side that does diffusion with this resetting with memory with a probability q, and at the origin, q is equal to 0. So when the walker visits the origin, it automatically visits that site or that site at the next time step. And so this reinforces a little bit more this central region compared to any other region. So the idea is a very simple way of adding a resource site in the system. So you have a heterogeneity, right? And so that heterogeneity is a little bit more attractive. And so the memory term that we had, which was Q, this capital M, actually, so that reads like this. And now, since Q depends on the position n prime from which you reset before reaching n, you cannot take it out of the sum. You cannot get rid of that joint distribution. So the system is no longer closed and becomes fully nonlinear. And so if we use a decoupling approximation, which I think is valid at t equals infinity. So probably we think actually that it is exact. So we no longer have diffusion, no longer have logarithmic diffusion or Gaussians, if not, but we have some non-equilibrium steady states with some certain correlation lengths. And this, for instance, this occupation probability P naught of the origin is different from 0. And satisfies a self-consistent relation like this one. And it is possible to show that if Q is larger than a critical value, that equation admits some non-zero solution. And we have basically, so for above a critical value, we have some localized states, whereas below this QC, there is a trivial solution, P naught equals to 0, as t goes to infinity. So we interpret this as a spatial learning phenomenon. So the reinforcement of some particular sites give rise to some localization and just suppresses and just arrests the diffusion process. And we interpret this like a spatial learning of the formation of a home range, and this is a non-localized phase, so the worker continues to diffuse, albeit slowly, but it continues to diffuse. And the QC is actually very simple. It's related to a very well-known quantity, which is the no-return probability of a simple random walk on the lattice, the Polya probability. If we assume that this movement mode is that, but can be generalized to a Levy walk or Levy flight, sorry, or any step length distribution. So in dimension 1 and 2, it will be always localized because QC is equals to 0. In dimension 3, you will have a transition like this. If we take Levy flights, so in 1D, we can have this kind of transition on the lattice. So these are the conclusions. So I just leave them as a summary. Actually, there is a very challenging problem, which is open, is how to study the first passage time statistics in this kind of problem. So that seems to have been trying for a long time, and this is to be really, really tough because especially we do not have this closure that makes things so easy to calculate the propagator in free space. So I would like to thank collaborators. Some of them are present in the audience and students, and thank you for your attention.
Okay, last 2 minutes of this workshop. Any questions, please?
Can you please go back to the slide where you displayed the square log?
So which one?
The probability of the large, yeah. This one maybe the one before. This one, okay, yeah, this one, the top. For anomalous principle, you say that. So is there an interpretation why we get a log n because of the random recursive tree? Do we get
the log. You mean why we have a log t? Yes, exactly. Yes, the basic idea is very simple. Yes, since you're starting again from any new run is starting from a previous run, so you have a unique ancestor. So it's like a tree problem. It's a bit different of the usual recursive tree in the sense that there are some weights, but it doesn't change that
so
much.
is it because we get in a random recursive tree, it's like a log n delay always happens. So because the height.
Yeah, exactly. So the height goes as a log of the number of sites of nodes, and then so that's a simple explanation of that log n. If the weights are more or less the same.
Yeah,
right? So for instance, if there is some.
Let's say we put one weight everywhere.
Yeah.
So everywhere we put a weight of 1.
Yeah, for instance, yeah. Of course, that can be modified. The weights are modified by the by decaying of memory. So yeah, and that follows everywhere in many of the observables like these large deviation.
you had a mysterious parenthesis that said that something was valid as long as the eighth moment exists.
Yeah, yeah.
But you didn't
So
comment on that.
Yeah, well, you'll have to ask them, actually. Yeah, that's a very unusual assumption. I don't know if something better can be done, but apparently that was really necessary to assume that. But it's very general. So as soon as this exists, so which means that the weights are not, yeah, the lengths are not very widely different. So we have this picture. Why it doesn't hold? Yeah, I don't know. That would be interesting to see. For instance, we have some power law distribution for the rand length. So some nodes start to attract many other nodes, and then that changes the scaling of H, the number of nodes, something like this. But yeah, I don't know in the detail why.
Okay, thank you, Denis.